Hello and welcome back to Code It Live. I'm your host for the day, Sam. With me, I have my good friend Matt. How are you, sir?
I'm doing okay. I was just on vacation yesterday, so I'm still a little bit on vacation time.
Yeah, doesn't hurt, doesn't hurt. Yeah, so folks, this is a different type of a stream because this is a user group meeting, a little bit formal. I mean, I put on a bit slightly better shirt, as formal as I can get from I'm still in my PJs. But this is our global app dev user group, and we do this once every month where we bring on an amazing person who's passionate about something. And I'm glad to have Matt with me today. So, welcome, folks. This is the global active user group, and actually, since I had Matt here, he has probably seen the whole evolution. So, fun story as to how we came to be who we are right now. Let's go full screen on this. So, this group was started back in 2008. This was Doug Meyer, myself, and a couple of other folks. We were all excited about Windows Phone. It was called Columbus or Central Ohio Windows Phone User Group. Then we spent like 3-4 years and we thought, well, let's evolve to Windows, generic enough. And then we started having a lot more, AR, VR talks and, voice assistants and JavaScript. So we're like, okay, let's just call it app dev, Columbus app dev, fairly generic. And then the pandemic happened and we all switched to, virtual things. And this group is still virtual. We'll still actually, I'll get with Matt because he's involved in the Columbus dev community. We still get together for, Christmas time. Otherwise, throughout the year, we are pretty much virtual. So we are now global app dev. And I like saying, like, unless we are all moving to Mars, I think we are safe with this name, this URL. So we are the global app dev user group. You can find us online and meetup sites, and we meet right here third Monday evenings on Twitch. And as I'm speaking, this is not the third Monday because clearly last week Matt was in a happier place on a cruise. I was at a conference, so we couldn't do that last week. So here we are, one week behind. We are still here. All right, so quick shout out to some sponsors who give us the tools and the technologies and the space to do this. I'll talk about Visual Studio a little bit more because we partner with them. We also like to mention some of the things that are going on around us. Even though we're global, Matt and me are both kind of in the heartland in the Americas. So we talk about some of the regional things that are going on around us, some dev conferences. Some might be on, either coast, but here's what's coming up. We have Connect-A-Ha. This is in Omaha towards the end of April. One-day conference, good speakers. Should be a good time if you want to head out, or if you're anywhere close to Omaha, Nebraska. We have Star Trek coming up in early May, and this is one that Matt's involved in. So, Matt, do you want to talk about this?
Yeah, Star Trek is another uniquely named event, which you're obviously familiar with your history of names. But it's a one-day conference in Columbus, Ohio, and it takes place in a movie theater. So after the conference is finished, we all get to sit and watch a movie together, and it's typically a Marvel movie. I think this year it's Guardians of the Galaxy Volume 3. I think I'm right about that. So
Yes,
great conference. Yeah. I definitely recommend it.
Yeah, I love Star Trek, and it's so nice to just geek out with some of your nerdiest friends over a Marvel movie at the end of a day of learning. So come and hang out with us in Columbus, Ohio if you're around. Tickets are on sale. It's coming up early May. Moving on to June, and there are way too many things happening in summer, so I'm kind of sticking to early May or June. We do partner up with Visual Studio, so if you're going to any of those conferences, and they do like a series of shows throughout the year at different parts of the country. We just did Vegas last week, but the next one that's coming up is also in the heartland, kind of a little south, Nashville, Tennessee. That's coming up middle of May. So again, this is a little bit more formal. It's almost 5 days worth of conference, great speakers from all around the world. So come and join. If you do come to Visual Live, you do get a discount as a user group member. And they do other shows. The other things that are coming up are in Redmond at Microsoft HQ. Then we go to San Diego and then Orlando. So pretty much all around the country. And then we have a big one. The slide is a little too dark here, I'm realizing, but that's their website. This is KCDC, Kansas City Developer Conference. This is coming up in late June. This has turned into a really big conference with almost 200 sessions from lots and lots of speakers, again from all around the world. So should be a good time. Again, all of these conferences, their tickets are open, so come and hang out if you have the budget, or if you have just a desire to maybe even spend a little bit out of pocket, but then come and really take in a lot of learning over a day or two. All right, and drum rolls. We do have Matt here, and I've known Matt for years and years. Amazingly swell guy. So I will let Matt introduce yourself. Caching is easy, right? Everybody gets it. It's the hardest thing in the world sometimes with software. So Matt, with that, I am going to give you the screen and bring up your desktop. All right, floor's yours.
Right, there we go. Well, thank you very much for that introduction. So today we're going to talk about caching, and the title is "Cache Rules Everything Around Me." If you, hopefully you get the reference. It's a Wu-Tang song. I'm not like a huge Wu-Tang fan, but I do enjoy this song, and I think the title really fits. So my name is Matthew Groves. I am, I have all kinds of job titles, much like the user group and Star Trek. Names for things are very hard. That's one of the other problems in computer science besides caching. But I'll call myself a DevRel engineer or developer advocate or product marketing manager, all these things that I do. Basically, what I really care about is helping developers do cool stuff and learn about cool stuff. So that's not really a job title, but my Wu-Tang name is Passionate Bravo. If you go to the Wu-Tang name generator and put in Matthew Groves, you're going to get Passionate Bravo. So thought I'd make note of that. Let's get on with it here. We talk about caching. Now we know that computers are fast, very, very fast. This computer I'm working on, presenting to you from, can run billions of operations per second. However, I/O is the real problem. That slows things down. Reading, writing to and from a disk, and that's any kind of disk, by the way, not just the old spinning kinds, but even the SSDs and thumb drives. It's still slow to read and write from them. And then if we bring in network into the equation, it slows things down. Reading and writing from another computer over a network. Even reading from RAM is slow. Looking at this chart here, compared to a L1 cache, reading from RAM is very, very slow. So the further away you get from a CPU, the slower using that data becomes. But a computer without input-output is pretty useless. We couldn't do what we're doing right now without input and output. So we have to read and write to disk. We have to read stuff over a network. Them's the breaks. But what's the problem? The problem is that time is money. And this is maybe a little misleading, this statistic here. I think it's kind of the reverse of this. The actual study says that every 100 milliseconds of delay reduced revenue by 1%. It's kind of the inverse of what's presented on the screen here. But the point is that fast enough is never fast enough. Time is money. So how do we make stuff faster? And I really think the simple answer to that is caching. Caching is probably the answer. If you're not already using it, it's something that's cost effective. Doesn't necessarily require major rewrites or re-architectures of your system in many situations. There's plenty of off-the-shelf solutions for adding caching to your system. So that's what we're going to talk about today. Now, I want to start out a little bit by just shining some light on all the places that caching already affects us. And it's already used in lots of places. And sometimes you don't even think about it. The caching is there because cache really does rule everything around us. So the CPU, I mentioned that already. The CPU has a cache built in because registers, if you get into CPU architecture, registers are the fastest, of course, but you can't have unlimited number of registers. So a CPU cache helps to speed things up. Your web browser, if you're viewing this right now on Twitch or some other web-based channel, you're already using caching, I guarantee it. The various JavaScript files and images that are present on your screen there are more than likely being written from a cache or read from a cache. Your Android and iPhone apps use a cache. Sorry, no Windows Phone mentioned here, Sam. But Android and iPhone are using cache. And I know this because I have to sometimes go in there and clear the cache on my Android apps to make them work when they misbehave. CDNs are a form of caching. These are serving up common JavaScript files to regions, get them closer to your house for a faster service. And a DNS is being cached on your computer. And oftentimes there are DNS servers that are caching only. So the very core of the web of the internet is run on caching. So I think we should understand caching a little better, know when and how to use it. And a lot of you out there are probably already familiar with caching and the basics of caching. So think of this as a bit of a refresher. I'm going to talk about some of the deeper things that you may not have thought about caching, some of the algorithms and some of the trade-offs and how caching works today. So we're going to talk about an intro to caching, because cache makes just about everything better. Both kinds of cache, really. Talk about how caching works and some common use cases and the architecture of those use cases. We're going to get into the details of reading from a cache and writing into a cache. The writing is really one of the hardest parts. And then, of course, as Sam mentioned earlier, is cache invalidation, one of the hardest problems in computer science. We're going to tackle that problem today. And I'm going to end with some of the trade-offs and gotchas you need to consider about caching, some of the speed bumps you might run into. So a little intro for me. I'm a Microsoft MVP. And also an author with Pluralsight, Manning, Apress, etc. I am, I'll just call myself DevRel Engineer is my current title at Couchbase. Couchbase is a database used by developers and technical people. So I'm kind of in a marketing organization, but I think it makes sense to have someone with a developer background in marketing, especially if we're trying to create marketing that's useful and informative for developers. Couchbase, by the way, is a NoSQL database. I'm not going to talk databases all that much, like detailed database stuff today. I will going to focus on caching, though, and actually Couchbase does have a built-in managed cache. So I'm going to talk about that in detail, because it's very interesting how that works and the various trade-offs that you can take into account there. You can find me on Twitter at mgroves. I'm on LinkedIn also at mgroves. And it's very early to bring this up, but it's something that if you're interested in C#, you should look into the C# Advent, csadvent.christmas. It's something that Progress has been kind enough to support this last season as well. So if you're into C#, definitely check that out, especially towards the end of the year. And you can participate in that if you're into C#. All right, so what is caching? Simple definition of caching is that it's a collection of duplicated data to serve future requests faster. That's really the simplest definition of it. It was, I wouldn't say invented, but first formally described by this guy, Maurice Wilkes. I'm kind of a little bit of a computer science history nerd, so I like to look this kind of stuff up. And he published a paper in 1965 that described caching. He didn't call it caching, but described caching for the first time. And you can link to that paper if you really want to read it. Warning, it's extraordinarily dry, very math-heavy paper that describes the concept of caching in a formal way. So it's not very long, but it's a very tough read. So just a little picture of a cache here is on the left. I've got records. That's the complete set of data that a system might use. And typically that's a database or something else like that. On the right is cache. That's a copy of some of the data from the records. In some situations, it may be all of them, but more commonly, it's a subset. Typically, the cache medium is faster to access than the records medium. That's kind of what makes it a performance improvement. But it's also usually more expensive, or at least more limited than the records medium. So for instance, consider a hard drive that has 16 terabytes of data on it. And consider a cache that has 64 gigabytes of RAM. Now, RAM is pretty cheap, but not as cheap as disk. And disks are pretty fast, but not as fast as RAM. So you can see that you're getting the speed of one and the cost effectiveness of the other, combining them together to get a better experience. So this is a fun little exercise I like to do, especially in person. But if you are in any of the chats, you can join in and give this a try. And maybe let's have Sam volunteer to do this live, if that's okay with you, Sam.
I am absolutely in, because I told Matt that I'll be your annoying sidekick all through, so throw it at me.
All right, so This is a very simple exercise to demonstrate caching. We're going to use PowerPoint as a cache, though, not any sort of fancy caching software, but just plain old PowerPoint. So I'm going to show a trivia question on the screen here. And Sam, I want you to find the answer to this trivia question. Hopefully, you're not a really big Wu-Tang Clan fan.
I am not.
Okay, good. This will be a good demonstration then. So what I'm going to do is I'm going to get my stopwatch here on my phone, and I'm going to show the question and then hit start on the watch, and let's see how long it takes for us to get the answer to this question. Okay, Sam? So you're allowed to cheat. You're allowed to use your browser or phone or whatever to find the answer. All right?
All right.
Okay. And we're going to start on 3, 2, 1. What year was Wu-Tang Clan formed? All right.
Oh, this is pressure.
And anybody in chat, feel free to type in the answer if you find it as well.
And shall I blurt it out if I find it?
Yes, please.
1992.
1992 is the correct answer. Yes. So we got that in 17.43 seconds. It looks like we got an answer of 1991. Sometimes I get that. I think it depends on the search engine.
Hello, Loka. Now I don't know who's right, because like my search engine is Bing, so not always accurate.
Wikipedia, I think, is where I got my information. So I think that's the correct answer. But let's just go with that for now. Right. It could be 91. Maybe they knew each other before then, but didn't officially come together until 92. Okay. All right. So it took us 17 seconds to get that answer, right? Now I've got the answer cached in PowerPoint. All right. So we're going to do it again. We're going to do the exact same thing. We're going to ask the trivia question and see how long it takes to get the answer. Are you ready to do this, Sam?
Okay.
Okay. In 3, 2, 1. What year was Wu-Tang Clan formed?
92.
Yes. Okay. So how long did that take to get the answer that time?
Because I already looked it up. It's in my memory, which is faster, but it's limited to how much it can retain.
That's true, but it's also right there on the screen in PowerPoint. So PowerPoint is our cache. So that was much faster because we had the answer cached. So that's really the core of how caching works, is it just gives us a quick access to some of the data. But here's the trade-off, right? I can only put so many Wu-Tang trivia questions on the screen at one time, right? Even if I had a really high resolution, at some point it's going to be, too much to fit on the screen, and it's going to be just as time-consuming for me to scan all those trivia questions on the screen on PowerPoint. I might as well just go and use a search engine like Sam did earlier. So you can see kind of the trade-off there. Now, we're going to revisit that limit later. We'll talk about cache invalidation and things. But we don't really need a cache dedicated to Wu-Tang trivia. What should we actually use caching for? And that's what I want to talk about next, is caching use cases. So there are a lot of use cases for caching. And if you can think of any, throw them in the chat there and share some of the use cases you think that caching might be good for. But these are 4 that I think are the most common ones. So we're going to talk about these in more detail. So faster database access is an important one. Efficient API usage, faster browsing, and the 4th one, which I think is a very interesting one that people don't think about too much, is maintaining availability, especially with microservices. So let's talk about faster database access. So the idea here is that if you're a database and you're relying on disk, disk is slow. And if you're reading the same data over and over again, that can mean accessing the slow disk over and over again. So why not put that frequently accessed data in RAM to reduce pressure on the database and disk? So for simple CRUD operations, certainly no problem to pull this off, put stuff in memory. A more complex operation, it might be more difficult to cache that, but at the very least, taking a lot of those CRUD operations out of the disk into memory is going to take pressure off your database and allow those complex operations to have more resources. So it's a good thing all around. Writing to a cache first and to disk asynchronously is one way to speed up those response times, but there's some trade-offs to that. We're going to talk about that in more detail later. Here's a quick architectural diagram, very complex box, arrow, cylinder architecture that we're all familiar with. But the idea with this is that where do I actually put the cache? Where does the cache live? So there's lots of options for this. One simple approach is to just use your app. If you have an ASP.NET app or whatever app, it has access to memory and it can store data in memory, and a can be a cache. And it can access the cache data right from memory, very, very quick. You can also have cache running on its own server or multiple servers, a distributed cache that sits between the app and the database. So that an app needs a read from the cache, it has to go over the network to do that, but it's still going to be faster than reading from the database, which has to rely on disk. And we could also put a cache in the database itself. Now, this is much less common. This requires the database to actually support that and have a managed cache, but it's another place a cache could live. And I'll show you an example of that one later. But so I wouldn't recommend using all three of these, right? You're not going to get much benefit out of going through three different caches, but these are three different options, and they all have different trade-offs and pros and cons of where you can put the cache in your architecture. Another use case is faster web browsing. We're probably all familiar with this as web developers, but any given URL that you look up could consist of hundreds of other HTTP requests for JavaScript files, static resources, images, icons, CSS, whatever. And those files don't change very much. So a browser can, once it downloads a copy of jQuery, for instance, do people still use jQuery? I don't know. I love jQuery, but I don't know if it's still that popular anymore.
Yeah, they do. That's the reality for a lot.
Yeah. So we'll just save that copy of jQuery to my local cache. And so the next time it's requested, it'll just be local. It'll be on my machine. I don't have to make a network request to get it. Same principle applies to CDNs and so on. But you might be asking, well, doesn't that mean I'm going to get a huge cache of files taking up all my hard drive space eventually? And yeah, kind of. We'll get to that question. So the architecture for this is a lot simpler. The cache lives in the browser, which is most likely your hard disk. It could be your RAM on your computer. Ever wonder why Chrome uses 1 billion gigs of RAM? This could be part of the reason. But that's where the cache lives in this case. And then it's going to be making those requests to the cloud there. The CDNs could also live in web servers. That's a form of caching that gets those files closer to your computer or closer to your region. That's a form of caching. Number 3 is efficient API usage. So this could involve performance issues, right? If there's an API that's over the internet, for instance, there's some latency that's being introduced there. And also this may be some complex calculations going on with the API that may slow things down. And on the flip side of that, it may also be, if you're using a third-party API especially, it may cost you money to make an API call. So if you're using Twilio or LaunchDarkly or something like that, where a single API call may cost a fraction of a cent or something. If you can avoid making one of those calls, especially like a read-only call, that's going to save you money to actually cache the result of that locally. So there's 2 things. This could help reduce costs and can help reduce latency. It could be one or both. So just as an example for this, if I wanted to do an expensive computation over an API, let's say the Google Maps API, actually calculating a route, for instance, in this case, from Shaolin to the New York Times building, that is a complex algorithm to find a path. And if you look up Dijkstra's algorithm or A star or whatever, those are algorithms that take a lot of computing power. But it's often going to be the same route, right? If I'm driving from this location to that location every day, that could be probably the same route. So it would make sense to calculate it the first time. That might cost some latency. It might cost some money if I'm using something other than Google Maps to do that calculation. But once I have that route, I can store it on my phone, for instance, in my Google Maps app. So next time I want to navigate that route, I can bring it up in Maps. Now you might say, what if there's construction or a car accident? And we'll talk about cache invalidation later. But you'll also notice Google Maps has some alternate routes that are in gray there. So it's caching multiple routes. So if there's a traffic incident or something, it can still use the other routes. If one route is, maybe there's a street closed on it, for instance, it could direct me to one of those backup routes. So the architecture for this is very similar to database, except that it could be a wide area connection in between your app and your API. So for instance, Google Maps could be the API there. So you could put the cache still in the app, just like you could with the database situation. Just like before. This is called close caching, by the way, when you have it right there in the application with you. You could also, again, just put the cache in its own server or collection of servers, distributed cluster of servers running separately from the app. So it's going to be a local area network call to that cache before you actually go over and actually make a call to the API. Now, the API could have a cache being used behind the scenes, but that really doesn't affect our architectural decision, because especially if it's a third party, it's a cache that's benefiting them, but it's not really benefiting us. So it might be there, but it's not necessarily relevant because it's beyond our control.
Hey, Matt, quick
Yeah,
question.
sure.
So when you talk about caching in the app itself,
Yeah.
I get that, but could you have other like cache type services or servers running on your machine, which is not, directly tied to your app itself?
Right. Yeah. So that you could do that as well. You could have, for instance, if you're running a web server or Windows server or Linux server, whatever, you could have a web app running on there and a cache service running on there. And so that might have, if we talk about some of the trade-offs for close caching later, that might have some uh, benefits to doing so. Yeah.
Yeah. And also, quick comment here.
Sure.
Hey, Tyndall. Tyndall is a good friend of mine and a friend of the show. Um, I'm confused here. So you talked about Staten Island to Manhattan. That's
Yeah.
like a 40-minute drive and in rough traffic. But Tyndall is in Sweden.
Uh-huh.
And he's calculating a path to Johannesburg, like as in South Africa. That's like in a whole different continent, and you can drive. That's quite amazing.
Could
You
you
know what?
drive to Johannesburg from? I guess you could,
Yeah, I
right?
think Europe and Africa are connected by land. There are some bridges you can cross.
Yeah.
Oh, and trivia question here,
Sure.
completely off topic, but name the longest bus tour you can take in the world.
Longest bus tour?
Yeah.
Oh, well, so I was in Manhattan recently for a bus tour during the St. Patrick's Day parade. That felt like the longest bus tour in the world.
So there's this luxury company that's coming out. I think they're operational now. I read it somewhere, but from Istanbul in Turkey all the way
Okay.
to London, UK, and they do that in like 16 days through like 20 different countries. It's a nice, very relaxed and luxurious bus, but it's a
Uh-huh.
long, long drive. Yeah.
It's like a
Oh,
cruise ship, but for
it is
land.
like a land cruise ship. And Finland is saying like through Egypt, so that's the connection between you go through to hop over to Africa. And I've been to actually Johannesburg. That's like the almost the southern tip of Africa.
Yeah, yeah, that's a long drive.
Yeah.
I often thought that I could maybe drive from where I live in Ohio down to South America until I actually looked it up and realized that there's actually this area that's just not drivable and really not passable by any humans, normal humans. So it's really not possible to drive that. You have to take a ferry around or something like that. More trivia, but yeah. The actually calculating those routes is very, very difficult.
Mhm.
It's a hard problem in computer science, and not really related to caching, but just an example of something that could take a lot of time or incur some costs. So. All right, sounds like a challenge. Yeah, right. Go for it. I think people have tried that challenge and they end up very dead. So at your own risk. I don't think even the Top Gear guys could do it. That's how challenging it is. So. All right, so that is the architecture for like an efficient API usage, I'll call it. The next one is, I'm going to call it maintaining availability. This is kind of related to microservices. It doesn't have to be microservices, but anything like a microservice type system where we have two different processes that are retrieving data from one or the other, one side or the other. And so this is similar to API usage in that performance isn't necessarily latency is not necessarily a big deal here. It's not a major concern, but we're using caching for other reasons. So let me just, I'm going to show you a diagram here. I think that helps illustrate a little better. So I've got a simplified example here. This is, let's say, a microservice architecture. I've got two different microservices. They have their own domains, their own databases. And the way they communicate with each other is over a network connection. So let's say one is a user profile microservice that has stuff like my name and my home address and things like that. And the order microservice takes care of my purchases or shipping my orders or whatever. This is some sort of e-commerce store, let's say. Okay, so in order to complete an order or ship an order, the order service needs to know my shipping address. So it's going to request that from the user microservice because In a microservices architecture, you have these data domains, and the order microservice or the user microservice is storing the address. The order microservice is not supposed to be storing the address. It's the user microservice is the only one that can manage that. That's just how you might design a microservice architecture. So order microservice has to communicate over the network to get that information from the user microservice. But what happens, because these are separate processes, what happens if the user microservice is crashed and it's down for seconds or minutes or hours or worse? If this is the only way they communicate with each other, that means the order microservice can't work either, because I can't get the address. And so therefore the whole system goes down because of one service going down, which is antithetical. Is that the right word? Antithetical to the whole purpose of a microservice system, is to have these independent autonomous services that can operate on their own. So one way we can address this is with caching. And I'm going to bring in a couple components here. The user microservice, I'm going to add some kind of pub sub system. This could be a Kafka or RabbitMQ or some sort of queuing or broadcasting system that whenever a user profile address is updated or is added or changes or something happens to it, we can then publish that and announce that to the rest of the system and say, attention, here's a new address for you. And you can subscribe to that if you want to. The order microservice can then listen for those events and say, oh, a new address. I want that information, just the address information, and I'm going to store that in my own cache. So now I'll start to build up a collection of addresses in the order microservice. And so what this means is that if the user microservice goes down for any amount of time, the order microservice can instead pull the data from the cache and keep working. So it becomes more autonomous in this way, in that it has more ability on its own to take action, even if the user microservice goes down. So that is what I'm going to call the maintaining availability use case for caching, because the speed here really isn't an issue at all. The cache could just be a hard disk, for instance. It doesn't have to be RAM. But the point is that it's my own copy of it. And if that copy, if it's in RAM and RAM is volatile, and if that power goes out or resets or something, no big deal, because the actual, the system of record is the user microservice. And so I can still pull that data later, and I can listen to publish events from that later. So it's okay if that data in the cache goes away. I can consider that ephemeral, and I can still make requests to the user microservice as long as that's still running. So this is a good way to provide that availability. Sorry, you had a question or comment?
No, for the haters of microservices, then a lot of good comment. Like it's you do an auth lookup and you have like 12. He meant like layers of service, but I think I like lasers more.
Yeah, I like lasers of service. That's good. Yeah.
Yeah.
Well, I mean, absolutely. So the point of microservice is sometimes missed in situations like this, where it's only this on the screen here, and that becomes a very tightly coupled set of services. If one goes down, the other goes down, and that really defeats a lot of the purpose of microservices. So it does introduce a lot more complexity, yes. So make sure you need that complexity. This is not a microservices talk, but make sure you need that complexity before you introduce things like this that you need in order to maintain availability. So, yes, I do like the idea of lots of lasers in my microservices too. All right, so those are the main 4 caching use cases that I see out there in the world. Maybe you have some more. You can add those as a comment there, or maybe if you can think of any, Sam, throw them out there. But these are kind of the characteristics of the use cases that I think you can look for if you think caching might be something to help you solve a problem. So if it's something slow, I think a cache is going to help you speed it up, or at least reduce latency. If you've got a constraint, like I'm only able to send 5,000 requests a month to Azure Cognitive Services, well, maybe this can help reduce my need to do so many requests. In the case of microservices, if your service can be disconnected and you want to maintain availability, caching can help you there. If there's lots of repetition reading from a database, caching can help there, and of course costs can help as well. Especially if an API read costs a certain amount of cents or portions of a cent, you can reduce the amount of costs on your bill for third-party APIs.
Yeah, indeed. Nothing to add, just an observational, because I was just talking to somebody today. We have a network debugging tool that's fairly popular among developers. It's called Fiddler.
Mhm.
And if you let it listen to network traffic for some of the highest usage websites like CNN.com, I was looking at that today, just to load up a single landing page, it takes roughly about 300 requests and responses before everything loads up and they have everything to show you the page. So they're not going to disk or going over the network for all of it. So this is definitely helping, trying to speed up what's already cached.
Yeah, absolutely. Yeah, there's lots of those modern websites that, in my opinion, they spend way too many requests to serve you up a simple page, and those do bother me. But yes, caching can definitely help in those situations. All right, so we know caching can help us in some use cases. We know where it might be useful. So let's look at some of the gory details of how caching works, and start with the basics, which is reading from a cache and how that process works. So it's pretty straightforward, I think. This is a fun little example here. We've got a Wu-Tang Clan lyrics database and a website that's the front end of it. And a user will come to the site and they'll request song lyrics for their favorite Wu-Tang Clan song. Now, of course, so we need caching for this because we want to make sure those lyrics are served up lightning fast. So we've got my code here. That's the first box. That's my ASP.NET application or my Ruby application or whatever. And someone's asking for songs there. I've got a cache set up with a couple songs already in it. And then I've got a database that has the entire catalog of songs in it. So let's just go through a few scenarios here. First thing is the user comes to the site and they want to look up the song lyrics for song A. And so my code will first go look at the cache, see if song A is in the cache. And if it's in there, that's what's called a cache hit. That's a good thing. Cache hits are good because that means it's less time spent working with the database or waiting on a disk. And so that can be served up to the user. Next user comes in, they want to look up song B. Similarly, we'll look in the cache first, and there it is. There's a hit for cache rules everything around me. And notice that in both these situations, we've not touched the database at all. So we've reduced the database load here by 100% so far. That's very good. Next, let's look up song C. So what happens with song C? We're going to look in the cache first. It's not there. So this is what's called a cache miss. When we're looking for data in the cache and we can't find them. So now we have to do a slower process. We have to go look at the database. And this is what I call the walk of shame. We have to go around the cache and go all the way to the database and wait on the database to look up song C for us. And it is a Brooklyn Zoo. And there we have retrieved it now, so we can return it to our user. We can also put it in the cache for next time. We can write it into the cache, and that's the next thing I'll be looking at is cache writes. But can anyone tell me what's going to happen if I go to look up song C again? Maybe you can chime in, Sam, or someone can mention this in the comments. What's going to happen this time?
It's a cache hit unless something changed.
That's right. It's a cache hit. So that's a good thing. So the first user had to take the hit of the slower lookup of the database, but the users after that will, at least immediately, will get the benefit of that being in the cache hit. Very good. All right. So I just glanced over that cache right there. I put a nice little double-sided arrow to show you that, oh, it's just right into the cache, no big deal. That's actually a lot more work and planning than a simple arrow diagram. So that's what I want to talk about next is writing into cache, because there are multiple methods of writing into cache. And that is the really important and one of the most difficult parts of caching is how we're going to do the writing. So remember that data is duplicated. It has to get in there somehow, right? So it's stored in, I'm going to call cache and record. So you can think of just RAM and database, but it doesn't have to be RAM and database. It could be something else, but you got to store it in the cache and the record. And then we have this thing called a system, which is responsible for keeping that cache updated. Now, for the purposes of this presentation, just think of the system as, the code that I'm writing. Although in reality, you probably shouldn't be writing caching code. You should be pulling something off the shelf to do that. And there's actually 3 methods, believe it or not, for writing data into a cache. And these methods all have their pros and cons. I'm going to cover them today. So one is write through, one is write around, and one is write back, which I think is the most interesting one and probably least utilized, unfortunately. So let's talk about those real quick here. So write through, the first method is called write through. There's 2 steps to write through. First step is system gets a new piece of data. So my code, someone's submitting a new user or updating their address, whatever. That's the first step. Second step is my system needs to write that information to cache and record. Let me get out my very, very heavy air quotes here, at the same time. That is how the write through method works. Now, if you've tried this before, if you've worked with distributed systems before, you know that literally can't be done. You can't write something at the same time as something else. So that actually consists of a series of steps. And so the first step is sub-steps, I guess. Write to the record, so the database or whatever, and check to see if that succeeded. Did that succeed? If not, then the whole thing fails. Bail out, error, the write didn't happen. It was not successful. Then we write to cache. And did that succeed or not? If that didn't succeed, then the whole write is considered failed. We have to bail out of the whole thing. There's an error popped up to the user. Hey, something went wrong with the system. And we have to roll back that write to the record. That's I said step 1 here. I really mean step 2A needs to be written back, or rolled back, I should say. So, and then if both those writes succeeded, and if we've gotten to this far, then the write succeeded. The whole thing succeeded. So this is kind of like an ACID transaction, this whole process, but it's a distributed system. So we have to be able to, in this case, probably an ACID transaction on the record, and then inside that transaction, write to the cache. And if that failed, then roll back the ACID transaction. So that is the whole process of write through. This is probably one of the most common. Do you have a question?
Yeah, question here. So, why would the cache write mean the whole thing failed? I mean, the worst is you'll take a cache miss the next time because it's just not there. But you could still let the operation go through, couldn't you?
Right. And so I'm going to talk about that in the other 2 write methods. That's kind of how they would differ from this method, in that they wouldn't necessarily care if both of them got written or not. So, that's actually one of the reasons, one of the things I want to ask with this is that why or why not would you use this method? What would be the benefits of this, and what would be the downsides to using this method? So, the benefit, I think, is that it's very, very safe. This is, if this succeeds, that write is going to be in your record and it's going to be in the cache. It's going to be like a guaranteed, it's in there or it's not in there. The reason you would want to use this system is because I think what you're getting to, Sam, is that this is introducing more latency. It takes more time for this to happen. When I'm performing a write, I have to wait on 2 different systems to be successful, possibly retrying this system. And I have to, have an ACID transaction, all that kind of stuff. So it introduced latency. So it can be a little slower, but that might be okay, because if our system is one in which there are way more reads than there are writes, then that's okay. This is overhead. That's just a small portion of what's going on. Not a big deal. We can go through this, and that way we're successfully written to cache and to record, and we're ready to go. For this one write may correspond to 1,000 reads, and that's totally fine. Another system is a write around. This is also relatively common. And so this is similar steps here. Step 1, they're all the same. Step 1, really. System gets a new piece of data. We're going to write to the record only in this case. So we're not writing to the cache at all. Now we do have to make sure that if there's anything in the cache for this record, that it has to be invalidated. So that means we're telling the cache, if we're writing record A to the record A, we have to remove any record A in the cache, any data A in the cache. So that step may be something that is deferred or batched up or something like that. It's not something we have to wait on. It just, we want to let the cache know that this record is no good anymore because we have an updated piece of data. So we're only writing to the record. So we're only waiting on that disk to happen. So why or why not use this method? Well, I think the main reason you'd use this is if you're writing data to the record that's not going to be reread right away. So I'm writing something to the database and I'm not going to read it right away. I'm going to maybe read it in an hour from now or a week from now or something like that. No reason to put it in the cache just yet. So this is going to be a lot faster, a lot lower latency than the write through method because we don't have to wait on the cache to write. So why not use this? Well, just kind of the flip side of that. If we do expect to read this data right away, then we're going to have to immediately do the walk of shame, and we're not really getting any benefit over the write through method. So depending on your use case, if you're not reading the data right away, this is a good way to do a write into your cache. Okay. And the last one, which I think is the most interesting one, I want to spend the most time on, in fact, is the write back method. So this is kind of the opposite of the write around, is that we're going to get a new piece of or updated piece of data, write it to the cache, and make sure it gets written to the cache, get a success message there. And then we're going to kick off a update to the record, but we're going to do it asynchronously. We're not going to wait on that to finish. We're going to put it into a queue or something, and we're just going to fire and forget. And then assuming that step 2 succeeded, we consider the whole thing successful. We're not waiting to see if it actually made it to disk or not. We're just firing it off, and then we keep going. All right. So what is the trade-off for this one? I think probably seems pretty obvious why you'd be afraid to use this one, right? Because what if it doesn't succeed? What if it doesn't write that record and then that fails? Well, then we potentially could lose data, right? If that cache, for instance, if the power flickers or the cache resets, that data is gone. It's not on any sort of persistent storage. Or what if it takes a long time to get written, right? And you know, we're proceeding as if the data is there, but it's actually stuck in a queue somewhere. So that would be the reason to avoid this. The reason you might want to use this is that this is going to give you extraordinarily good performance because we're only writing to memory, which is very, very fast. And we're kicking off an asynchronous operation. We're not going to wait on that. So the latency is going to be, this is very, very low. Now, the risk there of losing data, that's a pretty big risk. I don't want to take a chance to lose data. So there are some ways we can make this more resilient with retries and multiple writes. But before I get to those, I want to cover those because it's pretty cool the way it works. No matter what, there's always going to be a very tiny window, and it could be a nanosecond or it could be a half a nanosecond, where if the timing's right and the power flickers or someone unplugs a network cable or something, data could be lost. That's just the reality of write back, how it works. Now, if you're my age, I think, Sam, you're a little younger than me, but you probably remember this, is when you're in college, you're working on a term paper or something in Microsoft Word, and you're hitting, at least I was, obsessively hitting Control-S after every few words in my document because I don't want the power to go out or Microsoft Word to crash. In those days, that was more frequent. And my work for my essay is lost. So I'm hitting Control-S every time because I'm afraid of that. When I'm typing it into Word, that's just storing it in memory. It's not actually saving it to disk until I hit Control-S. Now, these days, we've got more advanced Word with autosave and things like that. But even that is not completely bulletproof. Sometimes I get these really bizarre messages from Excel that recovered something for me that I didn't really know I had was working on. But anyway, that's beside the point. The point is here is that is kind of the similar risk with write back, is that it's in memory and it's not being saved to disk until it's being saved to disk asynchronously. We're not waiting on that to happen.
Matt, quick question. On the write through, I understand what you're saying with distributed systems, but could you not really spin off a different process or a thread and do the write asynchronously on the other thing, and then if something fails, then you roll back the whole thing?
So you're talking about to write through here.
Yeah, where you're
Right.
writing at both places, but
Yeah.
like the C to C, could that
Mhm.
not be on a different thread or a process, and you continue as usual, and
Mhm.
then you hope that the cache gets written, but then if that fails, then you have fallback plans.
Right. So in that case, so you're asynchronously firing off a cache. So I'm not sure that for one, I'm not sure there'd be much benefit to doing that, because writing to RAM is going to be very, very fast, and doing it asynchronously is not going to give you much of a performance benefit there, I don't think.
Oh, I see. No, I was
But
trying to say, like, maybe it has more to do with the write back. Like, you write to cache and then you move on, and
yeah,
you hope that writing to disk eventually works. And then if it doesn't, then you have other plans to recover, because your data
yeah,
might be
yes,
inconsistent.
right. And so that's what I'm going to get into next, is some of those ways that we can reduce the risk of write back here. Um, it's not, it looks scary because we're just trusting that it's going to be fired and forget, but there's lots of ways we can work with that to make sure that, again, like I said, it's never going to be 100% guarantee, but we can get to a point where we're pretty certain that it's going to be fine, and not mathematically, but in reality, it's going to be fine. So we'll talk about that in a second here, but just want to wrap up these with a quick table comparing these all together. So the write performance of write through and write around is not going to be as good as write back, right? Because those are waiting on disk in one way or the other. The question then is the write integrity of them. So they're going to be write through and write around are going to be good. They're fine. What about write back? What's the integrity like there? Is this something we could even bother using? Because if this is only useful for a system where we don't care if we lose data, that's a pretty narrow set of use cases. But other than that, it's very good for a mixed workload. So if you're dealing with a system that has a lot of writes, maybe a 50-50 write, or even a 40-60 or something like that um, ratio, a write back is going to give you much better performance overall. And that's really the point of cache, is performance. So that's what we're looking for here. So this is where I want to break into a Couchbase as an example and kind of show write back and in action, because I think it's fair to call Couchbase a write back system, certainly by default. So it has its own managed cache built into Couchbase. So it's a database, but it has a cache built into it. And so this is a diagram from the documentation that covers how caching and persistence work in Couchbase. So basically, by default, it uses a kind of its own variation of write back, which is good for mixed workloads. One other thing I should mention, that Couchbase is cluster. I think I mentioned this earlier about clustering caching systems. So there's usually multiple of these servers that communicate with each other and coordinate. And that's the reason for the replication queue you can picture there. So data is actually replicated to other nodes in the cluster. But from your code, the application server, the data is written into that managed cache. That's the place where it goes. And once it's written there successfully, by default, Couchbase is going to say, okay, it's been saved. You can go on with your life. That's very, very quick operation to save something to RAM. The data is going to be queued up to written to disk. That's the disk queue on the right side there. It's going to be queued up for replication to other nodes in the cluster. The reason you want to do that is in case this node crashes or goes down, you have backup copies on other nodes. And then it's going to be written to disk eventually through the disk queue. So, but the only thing your application code is waiting on is that initial write to the first machine's managed cache. Now, in reality, it's a little more nuance and complexity to it, but that's generally speaking how a Couchbase architecture is working. So, again, we're back to that scariness of what happens if something goes wrong and it's not saved to disk. Well, Couchbase actually gives you a choice in the matter for every operation if you want to provide a little more durability. So here's an example in C#. This is the only code slide of the presentation today. So if you don't know C#, that's fine. Don't panic. This is pretty straightforward stuff here. I want to insert that Wu-Tang song into my database. I say collection.insert, give it a key, give it a value. Okay. And by default, this is using that write back approach. But I could be a little more explicit with my C# and specify a durability option and say, I don't care about durability at all. All I care about is pure speed. Durability level none. And that's the default setting for Couchbase, is be as fast as possible. Don't worry about durability. But I can have other options for that. I could say majority and persist to active, and persist to majority. And these are each going to give me increased durability options. So it's going to reduce my risk, but it's also going to reduce the latency a little bit. So there's some trade-offs to using this cache. So quick illustrations of this. I've got, this is a kind of a zoomed out picture of that Couchbase diagram. So I've got 4 nodes here in my Couchbase cluster. So Couchbase is distributed database. So there's typically at least 3, usually more servers that make up a cluster. And I chose 4 here because that makes the math easier for me for this demonstration. But it can be a bunch more, or it can be 3 or 2 or whatever. Okay, so this is the none option. With the none durability, it's only going to wait for the data to be saved to memory on one of the nodes. That's all it's going to wait for. Everything else, it'll be fired off asynchronously. Oh, I didn't mention, up there I've got 3 replicas specified. That's probably overkill, but again, it makes the math easier for me. So with 3 replicas, what that means is that asynchronously, it's going to be queued up to be saved in all these places as well. So 3 other machines RAM and 4 total disks. So in this situation, we know the data is saved to memory in one place for sure. Everything else is asynchronous, so we can't be 100% sure about it. What has to happen in this situation for data to be lost? What's the worst case scenario here that's going to lose us data? If anyone in the chat has a guess, I'll give you a second to.
I mean, is memory tied to node 1? Like if node 1 goes out, yeah, then you lose.
Exactly. So if node 1 goes out, crashes or whatever, before any of the data is saved to those other places, then we lose data. That's bad. We don't want that, right? So this is no durability guarantee here at all, right? So let's bump it up to majority. In this case, we wait on the data to be saved to memory on node 1 and node 3 and node 4. That's the majority, is 2 of the other 3. And the other ones, we don't wait for it to be happen, but they will be written to the other places as well. So again, in this situation, what has to happen for data loss?
I mean, now you're expecting all 3 nodes, 1, 3, and 4 to go down. That's a lot.
That's right. So if 1, 3, and 4 all go down, then the data is lost because it's in memory and it's volatile and it goes away, right? So, I mean, we've got some increased durability here, right? It's better than before. So if node 1 and node 3 crash, we're fine. We still have the data. We can recover from that. No big deal. But I know a lot of people have been burned by memory in the past. And if it's not saved to disk, then it's not saved, right? So the next option is majority and persist to active. And so now we wait on all this to happen. Majority of the cache, and as long as it's persisted to 1 disk, we're good. So now what has to happen for data loss?
Again, nodes 3 and 4. Well, I mean, it depends. Like, I mean, if a node goes down completely, I mean, 3 and 4, you lose the memory. But even if 1 goes down, you can bring 1 back up, but you still have a copy of the data.
That's right. That's exactly right. So it would have to be node 1, 3, and 4 would have to crash, and node 1's hard drive would have to be unrecoverable, destroyed, or broken, or whatever. And hard drives do wear out, so that does happen, right? Especially if you're a large company with lots of servers, statistically speaking, you're going to have servers going out, maybe hard drives failing every day, right? So that's a total possibility. But again, we have significantly reduced our risk of data loss here. And the last one, of course, it'll still be written to those, but it'll be written asynchronously. And the last one is persistent majority. Hopefully you see where this is going. Now we're going to wait on all these writes to succeed before calling it a success. And so now nodes 1, 3, and 4 have to crash, and their hard drives have to go out as well. Which, again, not impossible, mathematically speaking, not impossible, but this is something I wouldn't worry about happening too much. But the risk here, there's less risk here, but there's a lot more latency, because now there's 3 network hops and 2 network hops maybe, and then 3 different disks you have to wait on to finish. So there's a lot of latency we're introducing here for more durability. But and we have to wait on asynchronously. We don't have to wait on those. So you can see the trade-offs here is that, again, I think I've shown with the write back, you get a lot better performance when you have a write and read heavy workload. And with durability options, you can do this on a per operation basis. So you can even decide some operations are more important to be durable than others if you want to. So, but with these durability options, you can worry less about those edge cases. And so I think this is really something that's underutilized in the caching world, is to take this approach. And yeah, there's some mathematical possibilities of data loss there, but very, very, very small. And of course, we'll go back to this chart here. It's all about latency, I think, with caching. You know, we talked about the first operation being nanoseconds, then next one microseconds, then we're going to sub-millisecond, and then hundreds of milliseconds. But this is why increasing that durability in the distributed system gets increasingly slower, right? Those microseconds add up. Reading a meg from RAM is 250,000 times slower than reading from an L1 cache, for instance. And reading a meg from SSD is 12 times slower than that. So if we're willing to accept a small mathematical risk, we can get really good performance from our cache. So those are the cache write options, and those are all possibilities for your cache system. You know, if you're not sure what system your cache is using, it's probably using the write through, but it's something you can look into, like which write system is my favorite cache is using, and what are the options that I can play with to improve the latency there. All right, the last thing I want to talk about before we call it a night here, Sam, is a quick foray into one of the hardest problems in computer science, if that's okay with you.
We have all night and the rest of the year.
We'll need all night for covering all cache validation, but let's just go through it quickly here. So let's go back to PowerPoint as a cache. You remember the Wu-Tang trivia on there. Instead of just the one fact, though, let's fill it with some other trivia facts here. So now I've reached my maximum cache size of 5 with 5 trivia facts. Now, what happens if I want to put in a 6th trivia fact? My user comes in, requests another answer to a trivia question, and now I'm out of room in my cache. What am I supposed to do?
You toss one out.
Yeah, the answer is to pick one and kick it out. This is a process called eviction. We want to pick which value we want to evict to make way for the fresh new data. And that is where we get this quote, famous quote from Phil Carlton. If you have a funny variation of this quote, I see them all the time on Twitter. If you have your favorite, put it in the chat there, because I like to see those. But there are only 2 hard things in computer science: cache and validation, and naming things. We already covered naming things at the very beginning of tonight's session, but cache and validation is it's a real challenge, because how do you decide which one to evict? I mean, with this example, which one should we pick? I mean, we want to pick the one that's least likely to be used, but how do we predict that? Now, the answer is we really can't. So how do we make a decision on what to invalidate, or what data to evict? And that's called a cache policy. And so there are several cache policies. We're going to go over the most popular ones here real quickly. The first one is called LRU, least recently used. The idea with this one is to evict the data that hasn't been read, hasn't been referenced in a long time. There are a lot of variations, but let's just go through the steps here real quick, show you how this works. So I've got a cache size of 3, and I'm going to process those 5 reads and do the first one. And what we do is when we read that one, we put it in the cache and we say, this is a 0. This is, right now, it's the newest value, so we get a 0 on it. The next one we put in is B, and we give it the next value up, so it's a 1. So now it's the newest one that's been used. Then we go to the order at C is the next one. It gets a 2, and we keep going and so on and so on. If we read B again, we're going to bump that up to a 3 because now it's the most recently used. And so now at this point, when our cache is full, we have a D we want to put into the cache. Which one do we evict? And the answer is A. Yeah, yep. A has the lowest value, so we evict it. It's the least recently used. And we put in D with a value of 4. What happens when I want to do a read on E? Which one gets evicted next?
C.
Correct. C has the lowest value, so it gets kicked out next. That's how it works. That's least recently used. This one is only taking into account the reads, the times that data has been referenced in a cache. This next one, NRU, it takes into account both things, whether it's been referenced and whether it's been modified. And it takes those into account together. I'm not going to go, we don't have a lot of time. I'm not going to go through these in detail, but they each get a score. And when we want to evict, let's say put in a value F, we take one of the items from the lowest score, in this case, score 0, and we pick one at random, which is kind of fun. A or B, in this case. One of those we pick at random and kick it out and make way for F. So whichever has the lowest score. Now, what's interesting about this one is that if you notice, the ones that have not been referenced, not been modified, it makes sense from the low score. The ones that have been referenced and have been modified, it makes sense for them to have the high score. But this model actually values being read, being referenced, higher than being modified. So that's why D has a higher score than C. All right, and the last one I want to cover is cache policy of none, no cache policy, which is also a policy too. Don't evict anything. Everything goes into the cache, it stays in the cache. So then you might be saying, well, what happens if I run out of room? What do I do then? And the answer is you have an error message. Sorry, out of room. Now, why on earth would I want to do that for a cache? And this is where a cache becomes more than a cache. It becomes basically an in-memory database. And the reason you want to do this is to completely avoid any disk overhead at all for pure performance reasons. So instead of eviction, you're going to monitor things like how full is my cache? If it's 80% full, let's say, it's time to add more RAM to my system. And this is where a distributed system allows you to do that. You don't have to, put chips into a machine as it's running. You just add another system to the cluster and adding more RAM to the system. So this is only really useful when you have an extremely high performance system and you want to avoid the overhead of disk. There are a ton more cache policies. I'm not going to talk about these, so we're low on time, but if you want to learn more about them, it's really good bedtime reading to read up all the cache replacement policies on Wikipedia. I will point out that there's something called Bilott's algorithm, I think that's how you say it, which is not possible to implement. It's just kind of a hypothetical algorithm that is able to perfectly predict which values to evict. But there are some approximations of it out there with cool names like Hawkeye and Mockingjay. Also, machine learning would be a pretty cool way to kind of study cache eviction history and make predictions about what's the best one to kick out in the future. So yeah, cache invalidation is hard. Sorry, go ahead.
I was going to say, I've never heard of Bilott's algorithm. Why is it there if it cannot be implemented?
Well, so it's an algorithm in the sense of it's steps to tackle a problem, but it's just not possible because it requires perfect prediction, and that's just not possible in the real world. So it's kind of a measuring tool. It's kind of a how good of an approximation can you get compared to Bilott's algorithm. So it's really only possible to know in retrospect what would have been the best thing to evict, but obviously it's not good for us to predict in the future. So anyway, check it out. It's some cool stuff there. If it were me, I would treat it like encryption. Don't try to write your own cache policy. Don't try to invent your own cache policy unless you're in the cache policy business. Have someone else's implementation and use that. It's just a matter of knowing which one to use, right? And that I can't be prescriptive about. That's just depends on your use case and the amount of data you're reading and writing and when you're reading and writing it.
So what are some common ones you see people use?
Yeah, I mean, number one and number two are the most common ones that are just commonly used, or variations of these are the ones you'll see in reality. If you can even choose, sometimes it's just built in. Like uh, I think Couchbase actually is using NRU, for instance, and you can't really change that, right? Unless you want, there's open source component, you can go in there and change it, I guess, if you want to do that. But I say this for reference, just in case there is a caching system out there that allows you to choose one of these options. Just know the trade-offs of those different options and look into those policies, because if you are not careful, you can get yourself into some gotcha situations with caching. And I've got 3 quick gotchas, and then I'll call it a day. First one, this is the most common problem with caching, is figuring out how to size your cache. How much RAM do we actually need? The problems could be it's too small of a cache, which is the most common situation. Or alternatively, too big of a cache. I have too much RAM. I'm paying for RAM that I don't need. So the way you deal with this is monitoring, just trying to figure out the eviction rate, if it's too high or it's too low. Stuff's not getting kicked out because I have too much RAM, for instance. So there's lots of different sizing calculators out there, depending on which cache system you're using. So those can help guide you. I'll also mention one of the features that Couchbase has built in is the idea of value versus full eviction. So if we're doing a value eviction, it means we're going to kick out the data, but the actual location of the data on disk is not kicked out. That stays in memory. So that walk of shame becomes more of a jog of shame. So it's a little faster to bring it back into cache if we need it. As opposed to a full eviction where we just kick everything out, which obviously frees up more memory, but then of course it's a full-blown walk of shame. Close caching. We kind of talked about this already a little bit earlier, but the idea with close caching is you have the cache running in the process, or maybe even on the server, right? It could be a similar issue. It's running on the same server. Let's suppose we have a web farm, for instance. We have multiple web servers out there, and they all are running caches of their own, or possibly in a separate process, but on the same server. There's some that could lead to some issues. So the 4 symptoms of this problem is redundancy. So we get the same item cached on multiple servers. So it's just kind of a duplication, a little bit of a waste of resources. Hotspots. Whereas if it's just a luck of the draw type thing with your web farm, one of those web servers could end up using all the cache, all its cache, while the other 2 are mostly empty, right? So it's kind of not a very efficient use of those resources. Inconsistency, which is not the end of the world, but server 1 might have an older version than server 3 in the cache, for instance. And then availability, which is if that web server crashes, the cache goes with it, right? Now, in the case of, you brought up earlier, Sam, about separate process. Well, now it's just if the web process crashes, no big deal, right? The cache is in a separate process. But if the whole server crashes, then the whole thing goes with it. Right. So again, it's not like it's a data loss. It's just that now we have to build that cache back up. It has to, it's going to start cold. So the answer to that problem is use a distributed cache. So don't put the cache on the same server as your web server, and don't use your web server process for cache either. It introduces network into the equation. That's true. So there might be some latency there with a local network, but you can avoid these gotchas with that. And this is the part where I talk marketing, and you can use Couchbase for this as a great caching technology. A lot of our customers start using Couchbase just for the caching, but Couchbase is a full-blown database with JSON, NoSQL, has SQL as well, text search, analytics, eventing, mobile sync, all that stuff that eventually, like, oh, this is a cool cache. It's got other cool stuff in it. We'll start using that. Redis and Memcache are also popular choices for addressing this issue as well. Basically, a separate process on a separate machine to handle your caching. And the last one I'll touch on here is just a bad eviction policy. So this is not something I see very often, but it's something to be on the lookout for. Did you write your own eviction policy, for instance? Or do you have the ability to choose an eviction policy? I would just say don't do that, or don't write a cache if you don't have to. And then if you are in a situation where you have to, or you're at least having to choose an eviction policy. Again, it's back to monitoring and benchmarking. Look for hit ratio and look for latency. Those are going to tell you, if you're in the right neighborhood or the wrong neighborhood for your eviction policy. But I'm going to say that go back to gotcha number 1 first, cache size, because that's more likely the issue than a bad eviction policy. Again, unless you're writing your own for some reason. So, all right, that's it. I went a little over time, but I do want to thank you all for joining me tonight, and I want to thank Wu-Tang and Method Man for your help. Here is a bunch of references if you want to dive deeper into this stuff, and there is a lot of stuff to dive into when it comes to cache. Like I said, one of the hardest problems in computer science, but you can check out some of the papers here, some of the diagrams I pulled from this, and some examples in Python that are really good. Some of the Couchbase documentation that talks about durability and replication that are really good. Again, good bedtime reading material. But I can make these slides available that Sam can spread them, distribute them however he normally does for the user group. But thank you very much for your time today. And if you have any questions, throw them in the chat there, and I'll see what I can do to answer them.
Yeah, no, good stuff. And like you were saying, like this gets you into a spiral quickly if you try to understand all the nuances. And the last thing you mentioned, like with the no eviction policy, where you're just trying to do everything in memory, and that's a slippery slope as well. Like you can have replication across machines, but how much can you persist all in memory? Eventually, you'll have to write somewhere, and then you're back to the problems of optimizing it.
Yeah, I mean, like I said, that's not something I see very often. We do have some Couchbase customers who are doing just that for very certain and narrow use cases, right? So I would, they understand the risk going into that, right? So make sure you're not doing it just because you want better performance, but make sure you understand the risks of doing that and the ways to mitigate that.
Yeah, solid set of resources here. Chat room is chiming in here to give you a thank you. I'm going to try saying your full name here. Loka Samasta Sukino Bhavantu. I hope it's close to how you would say it.
Oof, that's way better than I would. Close.
Question here from 10x developer. You don't need questions. You're already 10x. No, it's a good handle. What's the difference between cache and event sourcing?
Event sourcing.
Yeah, I'm also wondering what do you mean by event sourcing? Maybe you can explain.
I mean, I can tell you my understanding of event sourcing. I'm not quite sure how I would compare it and contrast it with caching, though. Looks like you got the pronunciation perfectly, though. That's good.
Oh yeah, no, thank you. What's your take on event sourcing? What is the first thing that comes to mind?
So for me, event sourcing it's a pattern used in microservices a lot. It's a way of, so when you are normally reading and writing, let's say a record to a database, you have a row that represents my address, and then I make a change to that row, and I save that change to that row of data. Event sourcing is more like a history of events that put all together will construct the current state of an object. So that might, I think in my mind, it's most similar to like a bank statement. If you look at your bank account or your credit card account, you see the current balance, yes, but you see a history of positive, credits and debits that you can go through those credits and debits and balance your checkbook, and that should match the current balance. It's the same thing, but applied to, a complex entity like a user profile or an address or whatever is in your system, an order statement or something, where it's a collection of events that if you play those events back, they will construct the current state of the object. And so
no, I was going to say, like, maybe this has to do with that consistency that you're maybe shooting for, because like if you have a set of steps that you took on a certain object, and even if you lose your cache or you lose your disk, you could recreate that, rehydrate that cache if you follow those steps back.
Yes, that's one thing you could certainly do, and using a cache to store like the current state of the object might make sense, right? Because if that goes away, yeah, like you said, no problem. I can reconstruct that from the event history. Yeah. I don't know if I would use event sourcing as instead of caching. I might use them together. I just don't, the difference between them. I think that they're not at odds with each other. I think they're things you can use together.
Sure. Yeah. All right. This is good stuff. Yeah, and so, folks, you can find. Do you have another slide to close things out? Because otherwise, you have your handle on the top, mgrooves. So
That's it.
that's where you can find Matt.
Yeah, absolutely. Happy to talk more nerdy caching stuff. I skipped over probably another 10 minutes of notes actually. So happy to dive deep into this kind of stuff.
Yeah, that Tenix developer is chiming in to say, yep. Thanks for clarifying. Yep. All right, this has been really good, Matt. Thank you for taking an hour of your evening and doing this with us. And Tenix developer Loka and Thindel, everybody in the chat room, thank you for chiming me in with your questions. This is always fun. I got to learn a whole bunch of new things, so I appreciate this. All right, folks, I think this is the show then. This is it for us in the evening. Matt and I are on the same time zone, East Coast in the Americas. I can hear my kid coming back from swim and asking for dinner. So
Yeah.
I'll go do that. And whatever you folks are up to, hope you have a good rest of your day. And we'll see you right here third Monday next month for this user group meeting, and for other shows that we do throughout the week that'll keep on going. But yeah, take care, and be good, be productive, and we'll see you around. So thank you so much.
Thanks everyone. Thanks, Sam.